Okay, I think we're just about there. So, welcome everyone to this iteration of the ARCHER2 GPU course. Today we're going to focus on session 1 of 5. We've reorganized the course to split it over sort of 5 half days opposed to a sort of 2 to 3 day solid block of time. Hopefully that's a bit better for people in order to get you sort of able to do this around other commitments. Really, it's the aim of that. It's always good to get your feedback about these sort of changes, so please let us know during or at the end of the course. There's a feedback form that we send around how this went for you guys. So let me just check, share some screens. So yeah, I'll share that. Okay. Good. So in case everyone wants to know where all the materials are and what we'll be using for the course, this could all be found via the ARCHER2 website. You should have been sent links for this in advance, but just so everyone can find it in future if they get lost, we just click on training. So either that big banner or there's a training option up here. Upcoming courses is this GPU programming with kernels option. The 29th to 30th of October, the 5th to 7th of November. And all the details of the course are here. So yeah, we have 5 sessions. Today we're going to run from 9:30ish to around 12 o'clock. The second session will be tomorrow. It will be me again giving that session as well. And then my colleague Juan will be giving the other 3 sessions, the 5th to the 7th of November. The kind of plan for the course is today will be, so the first hour will be kind of an overview talk about GPUs and where they sit in kind of the hardware landscape of compute and sort of the motivation about their design, what they're really trying to address, how they try to address it, and a bit of sort of context around. We're going to talk about HIP programming mainly because we have AMD GPUs on ARCHER2, but as we'll see that the programming model is very much a carbon copy of NVIDIA's CUDA setup. So if you understand one, you should be able to make progress in the other relatively quickly. Obviously, there's some nuances between them at levels of support and how the compiler environments work, but actually the principles are very much the same. The nomenclature changes a bit, but actually they're quite easy to translate between. We'll then move on to a practical exercise today around moving memory and making sure that your understanding of where data is at any one point is kind of really embedded. And then tomorrow we'll get on to launching kernels and using that data we've moved to the GPU and understanding how to start doing useful work. Later on, the other data sessions will then move on to sort of more advanced topics. So things like what are the more subtle aspects of memory on a GPU that you can access? So constant shared memory, things like this. How can I allow the GPU to manage my memory for me so I don't have to do explicit movement? How does the GPU work? How do you work with multiple GPUs together, for example? Can we do something with MPI, and what do I need to do special about getting MPI codes and GPUs to work together? As well as things like how do I organize CUDA streams and graphs so that I can get the GPU to do lots of work concurrently and organize it in a semantically sensible way. Okay, so that's kind of a broad overview of some of the topics. Throughout this course, the materials can be found at this link here. Okay, there's a GitHub page that gets updated regularly and should cover everything that we're going to discuss. If you see issues or other things you want to raise about this content, please send us a message and we can all add an issue to here. We can try to correct things, fix typos, and that sort of stuff. We also have a course chat, which we'll be using, which is an Etherpad. So if people have questions, because we use these collaborate sessions, which we've joined into now to do the sharing, if questions get lost or they go off into the chat or change session or someone logs out and they aren't there, they may not be able to come back to them later. So we have this etherpad so people can just sort of type my question, and they're each highlighted separately, so we can come in and answer later as part of the next session or in a break or something like that when we get a chance to refer to it. Okay. The other thing to say is if you have any questions around the setup we'll be using, so we'll be accessing ARCHER2 today in order to do this work. So one question which usually comes up is everyone able to access and log into ARCHER2? So ideally, if everyone comes up or okay in chat. Hi Sam, was that a hand up for a question or just to say yes, you can log into ARCHER2? If you just type in the chat, that'd be great. If everyone else can just kind of put a +1 or something in the chat to say yes, you've got access to ARCHER2, you can log in and you're happy with that, or we will spend, and if people are struggling or okay, good, just say logging. Fantastic. Those of you, if you've not managed to do that yet, that's fine. We can spend 5 minutes making sure everyone can log in and access. It's just important we just start that now, else we'll get into this. It won't be important immediately, but later on today, we're going to want to have people on. Okay, great. Okay, you've not logged on before. Okay, so if you should have had an email around how to get access. Jeffrey, who's going to be here, who I should have introduced earlier, is going to be here to help out in the chat and answer any questions. He will be able to help you log in. So there is an option to sort of have one-to-one communication, or you can have it go on in the main chat. Is that okay, Jeffrey? Can you give some assistance to people?
Yep, I will do that.
Fantastic. Okay, good. So everyone's logged in, and we're not as please just message Jeffrey here and we can try and help you out to make sure everyone has the access they require. Okay, final bit of admin. There is fantastic. There is also the ARCHER2 documentation, and I would strongly encourage you to read the documentation because we put time into it, but more because it is quite useful to understanding more about what we'll be discussing and the specific setup we'll be using. So while I'll cover lots of experts from this material as part of the course anyway, if you feel like something's not been covered in detail, or there's a question you have, or there's something useful to learn a bit more about this particular setup we have on ARCHER2, maybe we're not covering the particular thing you may be interested in for your wider work, there is documentation on the ARCHER2 docs site, on the GPU partition, a lot of detail around different compilers and setup. So so things like what combinations work and don't in terms of the compilers that are supported, certain detail on getting different codes running. We're not going to talk about Fortran, for example, a lot today, but there's some detail about how to get Fortran up and running. Yes, I just wanted to flag that there's also another reference that if you are between sessions during this course and have questions, or I'm more than happy to answer emails if people want to get into contact with me about anything while this course is going. But if you want to try and work stuff out for yourself or want some extra reference to read, this page exists within the ARCHER2 docs as well. So just to flag that to you. Okay. Are there any immediate questions around any of that? About setup, what the plan is, or anything else? Fantastic. Okay, so to start with, I will be giving I've got a presentation to give to kind of go through some the broad picture, and that will be sort of the next hour. So how do we want to share this effectively? I think Sorry, multiple monitors, single monitor trying to get sharing to work while I'm also trying to see all you is always fun. Okay. I think I'm just going to have to do the slightly janky way where you're all going to see yourselves for a moment. Oh yeah, I can share this this documentation. Look, of course. Sorry. Let me just stop sharing for a moment. Do that. That's documentation. This is the link to the course page. Okay. I'll click the links as well. Here is the course chat for you all, if you want to ask questions. And here is the course material page, which we're going to be cloning and using. That's a particular branch that's been organised for this session, but to be honest, the it's just one README that's been done, so you can just take the main off there. I think it'll be fine as well. Okay. Okay. And everyone, I can't see you, so I'm afraid if Jeffrey, can you just confirm you can see that screen and that title slide?
Yes, yeah, I can see the presentation.
Sick. Great. Okay, so yeah, so all this material is on Creative Commons license. So obviously, if you feel free to reuse if you find it useful, but please share a accreditation attribution even if you would. This material has been supported by UKRI and the Engineering and Physical Sciences Research Council and Natural Environment Research Council as well. Obviously, we're EPCC based at the University of Edinburgh, and HPE are our vendor partner that supply the ARCHER2 system, the hardware and the integration software that goes along with that. They're also part of the service, so they help to provide support for various aspects of the systems. Okay, we've kind of gone through preparation, so you should all have access to a project TA217. You should have set up safe and have SSH keys and be able to log in via your terminal. So we will need to be doing programming via the terminals. This, if you've got your own setups for SSHing in via IDEs and things like that, we can only provide limited support. So be aware that we, just because the plethora of different ways people can do this, we cannot reasonably support everyone. So if we will be able to help you with sort of terminal access and things like that, but beyond that, if you've got strange MoGRX term and other things set up, then that might be slightly challenging. We'll do our best. Okay, so as I've said, this is 5 sessions over the next sort of 2 weeks. The aim of this course is really to leave you with a broad understanding of why GPUs can offer an advantage over CPUs in certain cases. Understand how we're going to move data from host to device, get the data to where we want to do the work, know how to write kernels, and how to run code that executes on the GPU. Understand a bit about occupancy and why this is important to drive performance on the GPU. Try and introduce you to the various types of memory spaces that a GPU has, which is a bit more complicated than the CPU space. And get some practical experience implementing kernels and collections of kernels, operating as part of a stream, graphs, in order to try and gain some additional performance. Okay, so we're going to talk initially about the performance model, and then we'll talk a little bit about the hypercomputer programming model. We'll probably get onto memory management today. Might bridge a bit tomorrow morning as well. I think I'll probably start doing the exercise today, and I might show the solution tomorrow morning first thing. We will then look at executing a kernel and how to get things running, and we'll probably spend a bit of time focusing on that and looking at different ways to do that in detail. Talk about some performance considerations, and then we'll go on to look at managed memory. So how can we allow the GPU runtime to manage our memory movement for us, and what are the benefits and limitations of that decision. how do we use shared memory, constant memory on the GPU, and then streams and graphs. And then finally, some things about device management itself. So what if we use more than one device? So here's a rough breakdown of the schedule. Like I say, this was previously a 2 to 3 day course. So whether the topics exactly land where they're going to, we'll see how far we progress at the time. But hopefully this will allow enough space to kind of delve into the detail and try the exercises. So we will have sessions where it's kind of you guys trying something out, and we're going to be here able to support you. There's no requirement to, if you finish things early and it's kind of the end of the session, or there's going to be a break coming up, there's no need to hang around unnecessarily. But the point is we're here to support and answer your questions throughout the course. We'll be online during these times to help you with those particular exercises or answer any of the questions you might have. So I've provided these links in the chat already, the top two at least. That's the course material and the documentation. There is further documentation online around HIP at this location. We are on version of ROCM, which is 5.2.3. Okay, and there is a specific, so you see where this is sort of ROCM docs, amd.com projects HIP and its latest. There are sub versions or an archive of older versions which are specific releases. So we're on that 5.2.3, I believe. But you can check this because the modules on ARCHER2 will be named for the version. There's equivalent documentation for CUDA. Like I said, you should be able to apply many of the techniques and things we discussed to writing your CUDA programs as well. Pretty similar in that design. I've also linked two GTC conference talks. So this is NVIDIA's sort of annual big showcase conference that they do. And there's a gentleman there called Stephen Jones who tends to give a quite nice overview talk of GPU programming, the design decisions behind CUDA and on the offloading model and things like this. I think they're quite nice sort of hour-long videos that you can go and watch. If you want a little bit more of an understanding about sort of how some of the design decisions are made and why you're getting performance in certain ways, that's someone who's worked developing CUDA for a long time giving some talks. So that's another useful reference if you're interested beyond what we'll talk about here. Okay. So first, if we're going to discuss before we start deciding if we're going to program using a GPU, we need to decide why we might want a graphics processor. And to motivate that, we probably need to start by discussing some of the performance considerations in high-performance compute. Okay. So a simple model of performance in a computer might be something as simple as this diagram on the right. We have some processor and we have some memory. Okay. We need to move data from the memory into the processor to do some work and move it back. And there's a number of different factors which can be taken into consideration when we're thinking about the performance of how this system operates. So we have clock speed, the rate that we can issue instructions on the processor, so the rate in which we can do things, or each floating point unit can operate at. Memory latency, the time taken to retrieve a data item from memory to get it to the processor. Memory bandwidth, the amount of data transferred in a given unit of time. And parallelism, can we replicate this basic unit in order to do it more? Have more of them so we can do more things simultaneously. Okay. There's another sub-question to that is, can we actually take whatever we're trying to calculate and do it simultaneously? That's an entire incredibly challenging field on its own, but let's say from a hardware perspective, can I replicate this basic unit? Okay. So what I'm going to talk about here a little bit is what we've seen trends of in sort of the environment. Okay, so this is a plot of a spec and performance measurement on hardware through the years, and what you see is in about 2004, you see the advent of multi-core processors. I am old enough to remember when the Pentium 3 and Pentium 4, I'm not that old, but that still feels quite far back now, and these were single-core processors with very high clock frequencies. And at some point, that broke down, and you couldn't just keep increasing the clock frequency. So what you did instead is you started having multi-core systems, and you see that this switch to multi-core hardware kind of left you a little bit behind in terms of the projected performance. You're not on the same trend line in effect. Okay, so why would we not just keep increasing clock frequency? What's the fundamental limitation which something is doing this? Because that's clearly a better, it's going to scale better performance over time. Is it due to Moore's law? Everyone endlessly quotes that Moore's law is going to come to the end. It's been told it's coming to the end for at least the last 15 to 20 years. When this kink in this graph happened in 2004, 20 years ago, everyone said this was the end of Moore's law. It was not. Moore's law talks about transistor density, not about performance increases. So we've still got more and more transistors per unit area of a particular chip. Over time, that has not let up. Okay. So you'll see in the top right-hand corner of here is AMD EPYC Rome. That is the CPU in ARCHER2. So that's 2020 technology. Okay. And on the bottom left is an Intel 4004, so from 1970. So this is 50-year time span. We've continued to get the density of transistors we need to make more complex chip architectures. The real limitation of my background, as I'm a physicist by trade, is thermodynamics, which is usually the limitation for limit well everything. And what you see is fundamentally the issues around power. And you can't reasonably keep increasing the clock frequency of your processor and still expect to be able to deal with the power consumption. So this plot on the left is really saying this is what happened to clock frequency at the time. We hit a limit. 3 gigahertz really is as far as anyone bothers anymore. You did have some systems that tried to push up to sort of 4 or 5, but that never really caught on commercially in the long term, just because the power consumption was too high. Your issue really is actually around cooling this. So the plot on the right here is talking about sort of the different sort of scales of temperature you see with processors. So the red plot is different processor architectures. So again, you have this Intel 4004 at the bottom left. This is this 1970s Intel chip, and this is Intel chips moving forward right up to sort of mid to late 90s as the Pentium 4. And your temperature these things are operating at is somewhere the power density between a hot plate on the top of an oven and a nuclear reactor. So you have to cool that sort of wattage per square centimeter all the time. And is that an efficient way to try and get your computation out? So the equation in the top right says the power is related to the voltage squared times the frequency. So if I reduce the frequency, I can do something about the voltage as well, and then I can gain some benefit in terms of the total power can halve. I can still, then if I can halve the power usage, maybe I can double the number of transistors in a particular location. So actually I can use that additional parallelism to get back some performance. It won't scale quite as well as the just increasing frequency, but at least it means I'm not having to call something that's incredibly challenging in terms of material science and how I actually build these constructs. Okay, so in the bottom left then, what we're doing is trading this time per cycle frequency. I'm sorry, I should start again. A runtime in a program can be determined by the instructions, the number of instructions I need to do per program, the cycles I need to run per each instruction, and the time per cycle. So if I increase frequency, then this increases I can speed up things very easily. I don't need to reprogram or reorganize by my particular simulation. I can just crank up frequency, everyone's happy, you get more performance without having to change your code. Okay. Sadly, this comes to an end, we have to do more parallel computing, but you can see here is if I can find a way to do those instructions in parallel, I can also get some performance. Okay, this isn't really related. this kind of motivated why we've ended up in the sort of GPU space. So we've ended up in a world where multiple cores are now important to get additional performance out of our systems. So I've talked a lot about clock frequency here. This single plot is kind of this overall picture where you say, well, actually, transistor counts continued up. So this is kind of all these plots have shown from a single diagram. The transistor counts continue to increase. Single-threaded performance, is kind of plateaued very slowly. It's not kind of increased because of frequency. That's plateaued a long time ago. Typical power has stayed capped from relative to these systems because you just can't cool it, but the number of logical cores has actually increased a great deal. So you're getting your performance by increasing. Still, the density is increasing, but you have more cores to play with. And what we'll show is that GPUs are just a natural continuation of this trend, really, and it's just how you start to organize the computation differently, which is the real change here. Okay, so that's sort of a long sort of introduction there to sort of motivate why this particular design has been chosen, and why we've ended up in this parallel space. GPUs really just take this parallelism to sort of an extreme effect. If anything, they continue the trend by reducing clock frequency even further. Okay, so yeah, so without some fundamental breakthrough, we do not expect clock frequencies to any way to be able to deal with the power density. So we don't expect that to increase any further. So we really are limited and have to find a new way of computing. Memory latency is another serious concern. So it may take sort of 100 to 1,000 clock cycles from a standing start to retrieve a piece of data from memory to get it to the processor. So there's our simplistic model, processor and a piece of memory. If we're going to say we can do an instruction per clock cycle, but it takes me 100 of those, 2 orders of magnitude or 3 orders of magnitude more to go get memory. Actually, getting memory is maybe my biggest constraint in these systems. So if everyone could log into ARCHER2 and do LS CPU for me and post what the sizes of the different caches are on the login node. So if you look to run LS CPU, when you log in, and tell me put some information around the particular setup. And I will, so just to break this lecture up a little bit. If I can stop sharing weird stuff, that'd be great. Okay, I'll just stop sharing for a moment. Okay, so post in the chat what you find. And we'll get going again. Yeah, great. Okay, fantastic. Good. So we have a nice little hierarchy of sort of 3 caches. It's LS CPU. Yes, sorry, I realize I've given the I've moved the slides away. I can't see you and see your response at the same time. Right. Good. Okay, so most people have seen that. I will share my slides again. Oh, great. Apologies for that. Too far forward. Okay, fine. So, so CPUs try to mitigate. So why do we care about this cache hierarchy? So we're trying to minimize latency to go and access some memory in order to do some operation. We can only do operation if we've got the useful data we want to do operations on available to us in the processor. CPUs approach this problem by having caches. So this is memory that are close to the processor. They're quite expensive. They're usually relatively small, but they've grown significantly. So L3 that's half is quite big. But that's shared between on ARCHER2, that's 64 cores have got to share that. Okay. The idea is this hierarchy allows you to smooth this access pattern. So you can pre-state stuff that you can go fetch in advance to have stuff nearby. And if you're going to reuse data, then that's effectively, and you write code to reuse data effectively, That's a good way to try and minimize this memory latency as much as possible. Okay. The other key consideration is memory bandwidth. You are almost always limited in your applications by your ability to, is not by the flop count you have. This is usually the worst quoted thing ever. People go, my CPU or my GPU has this many flops. Your applications are never usually bound by flops. They're usually bound by your ability to go and get all this data. So latency is how long it takes to get something small within a single grab, so within a single cache line. If I've got some larger amounts of data, bandwidth is what's going to be limiting me. This is all offered within the order of 100 gigabytes. On commodity DRAM, sorry, that's not what I wanted to say. The capacity of your RAM is usually of the order of 100 gigabytes in current systems. GPU nodes on high-performance computers are reaching around the terabyte of memory available. The maximum memory bandwidth is usually limited to sort of 100 gigabytes for commodity CPU-based nodes. So ARCHER2 is about 200 gigabytes across the whole node of memory bandwidth from the main memory. Applications are always usually limited by this bandwidth. On the right-hand side, we have a roofline plot, which is showing two different regions. So you have this horizontal line, which is your peak flops that your system could produce, and you have this diagonal line, which is your memory bandwidth you're going to get in gigabits per second. And what you're trying to do is maximize the arithmetic intensity. So if you have it, you can profile your code and put a point, profile a function within your code and put a pointer on this graph. And almost certainly it will be on the left-hand side of this dotted line. That's the bandwidth bound region. Okay. Therefore, memory bandwidth is crucial. It's a crucial consideration for trying to increase performance. This is something GPUs try to address directly in their design. Come on to have a look at hardware in a moment. Okay, so then also we talked a bit about parallelism. So the number of cores in a ARCHER2 node is, you can run out a CPU again to look at this yourself, or you can look at the output, but it's sort of 64 cores per socket, and there's 2 sockets per node. So you've got 128 cores which you can do things independently and work on and do stuff in parallel. So if we can't increase this clock frequency, we're going to do our damnedest to use as many cores as possible. But we're still limited to this order of 100 cores. Okay. Until about 5 years ago, so 10 years ago, this was well under 100, or sort of 50 cores per node. So it's taken sort of over the last decade to really push towards 300 per node. I think that we just recently bought a system which has got 288 per node, for example. But where you might see additional parallelism is from a GPU that has thousands of cores. So we're really going to push the parallelism up greatly by moving to GPU hardware. Okay. So I've done a lot of talking and setting the scene there. I'm trying to explain a little bit about the context in which motivated sort of our decision to sort of move to GPU processing quite heavily. Initially, this was driven sort of by commercial interests. If you've a lot often by gaming, if you're trying to process sort of pixels on a screen, it's not very computationally intensive to work out what color should be in a pixel. But I need to do a lot of them very, very quickly because my response time has to be very, very short. The time it takes to render that particular scene, that particular image, especially in a game, where I don't necessarily know what the action is going to happen beforehand, is important in order to give a good experience. So that's driven this architectural design to say, well, we can have a lot of maybe less performant cores, but I can produce a whole lot more of them. Again, to this frequency argument, GPUs tend to operate in the 1.4 or maybe 1.8 gigahertz range. So almost sort of half of what a CPU might, or around a half of what a CPU might typically operate at when boosting. Again, this helps you deal with that power management issue and have more cores available to do operations which are parallelizable. I can render each pixel independently. There's no dependency on each other, the neighbors, so they can all happen simultaneously. Yeah, so memory latency has not gone away. What the difference here is that GPUs have made a decision to address memory latency differently. What you effectively have is latency hiding in GPUs. CPUs try to do latency minimization. So you get a benefit from a GPU when you have a lot to do because you can hide the impact of latency. If I need to go out to memory and get some data, what a GPU will do is it will have enough work to be able to say, well, you've stalled, you're going out to go and spend 100,000 cycles, 100 cycles or 1,000 cycles going to get memory. I've got another bit of work ready to go. That bit of work is going to jump in and start now. And GPUs are very, very effective at moving new pieces of work in and getting them running while other processes are going to access information or stored or stopped. And this hides the latency we would see normally by not having more detailed sort of a deeper cache structure that you might see in CPUs. So they can be much simpler in terms of the units of operation, and therefore it's easy to duplicate. You also see typically much higher memory bandwidth. Okay, the capacity of a GPU up until 5 years ago, a V100 GPU, so a Voltaire, was about 16 gigabytes. There was some variants which are 32 gigabytes. Really towards the end of the run, the sort of modeling of that was a 32 gigabytes device. This was not quite enough memory to have available. You were constantly going back to the host to get memory and pull it back, and that was relatively slow. It still is relatively slow. But what you see now is you have sort of orders of 100 gigabytes of memory per GPU. So you've got more capacity. More importantly, the access speed is all much faster. So your bandwidth is your order of 1,000 gigabits a second. And this is the type of hardware and the way that the memory access is organized allows you to get these much faster memory access speeds. So if the majority of your scientific codes or most programs are limited by memory bandwidth, offering an order of magnitude improvement in memory bandwidth access is a huge performance improvement that you can get if you can port your code to a GPU. So for example, taking that ARCHER2 CPU node example, it gets you about 200 gigabits a second of memory bandwidth. A Grace Hopper GPU, superchip device, operates its GPU memory bandwidth is 4,000 gigabits a second. So there's a factor of 20 on offer. If you can access it, you won't get it all, but even if you get half, you potentially got a factor of 10 in your memory bandwidth. So a factor of 10 could translate into your performance. That could be revolutionary for a particular application you're trying to run. Yeah, so again, the core count, the parallelism we're able to access with these systems, we don't have hundreds of cores, we have thousands. Okay, I think I'm trying to remember the exact statistics off the top of my head, but it is many thousands of cores are available. I'll have to look up the exact value in a moment for the particular GPUs we'll be using. But again, you've got orders of magnitude more cores to run simultaneously into useful work at the same time, and that can be immensely beneficial if you can effectively program them, which is what we're going to be talking about during this course. Okay, so how is the hardware organized for the GPU? So I'm going to talk about a bit of a nomenclature here. Some of the phrasing is a bit, I find, annoying and clumsy, but it's what the vendors refer to in the documentation, so we will use it to make sure it translates easily. If you look up their other courses of the material. So cores on an AMD GPU are organized into units. These units are referred to as compute units, or CUs. Okay, each CU or compute unit contains many smaller processors called streaming processors. Okay, this is particularly egregious, and I'll give you the translation below around the trend between AMD and NVIDIA. these processors, these stream processors, are responsible for carrying out the mathematical operations that are required for tasks such as rendering graphics, encoding video, performing scientific calculations. Okay, these are the cores that do the work. Okay. Each AMD Instinct MI210 GPU that we have at ARCHER2, we have 16 of these GPUs. There's 4 per node. There is 104 compute units. Each compute unit has 64 stream processors, which means we have 6,656 stream processors that can work in tandem on a GPU. So now compare this to your ARCHER2 CPU node, and you have 128 processors. So you get a huge factor in just the amount of work that could be done simultaneously. Okay, I've provided a link here for more detailed overview of the particular GPU and some more details about it. The other important thing is this translation between AMD and NVIDIA. And in most things in GPU land, standardization is a challenge because everyone's still competing so much. It hasn't got to a coming together of sort of wording or ways to define these things, unfortunately. So if you read NVIDIA documentation, a compute unit is a streaming multiprocessor. Okay, and this is the most confusing, but I think a stream processor is a CUDA core. So try not to confuse a streaming multiprocessor and stream processors, because they are at different levels. A CUDA core is the same as a stream processor, so this is an individual core that's sort of physically on the hardware, or a single thread of execution is the simplest way to think about those two. You also have wavefronts and warps. Okay, we'll come on to these terms more in a bit, but the best way to describe a wavefront or a warp is a group of threads executing the same instruction. Okay, and I'll show you some diagrams of the hardware about how we group instructions and how this looks in detail. But those wavefront and warps are equivalent. And then we also have work groups in AMD parlance and blocks in CUDA language. Okay, and this is about some space of execution you're going to work on. So you might give a block to a wavefront to execute. So there is a block of work, and a particular wavefront is going to, or warp is going to do that work. That group of threads, or CUDA cores, or group of stream multiprocessors in a wavefront or in a warp is going to do work, is going to execute the work given to it as part of the block. Okay, sorry, I'm going to have to move around to see people's questions. Yeah, exactly. What's left of the array is what is called by AMD, and the right of the array is what's called by NVIDIA. I know I've repeated this a lot. It's just the jargon that can be very confusing if that will be used pretty frequently. Great. Okay. Okay. So let's look a little bit more detail about what a compute unit or stream multiprocessor might look like. So this is a diagram from NVIDIA. This is a diagram from a A100 GPU. So on the left-hand side, you can see a single stream multiprocessor. It has a number of different elements here. So the key thing to sort of notice is that you have, in the blue, you have some different caches. The green are different types of floating point unit. So you have tensor cores, you have integer cores, you have something parts that do FP32, and you have some bits that do FP64. Okay. The total number of registers per SM for this particular GPU is 65,000. The max box of work that a stream multiprocessor can do is 32. The maximum number of threads that a stream multiprocessor can work is 2048. And then you can see that each sort of warp contains 32 threads. This is 32 cores of execution. You can only have 4 warps concurrently active at a time. And this 32 threads of execution will be coming related to the number of FP64 cores that are available. You have some detail about the memory bandwidth you can get per stream multiprocessor. So I talked about there being 4,000 gigabits per second on a Grace Hopper. That's for the whole GPU. If I've got a lot of stream multiprocessors, it's going to be divided up. So I've only got 90 gigabits per second. Okay, this is an older piece of hardware, but this is indicative sort of ratios you might expect. And you also might see, which kind of makes sense, right? You kind of had order 100 SMs or compute units per GPU, and if I've got 4,000 to split between them, okay, it's a bit higher than I'd expect, but it's that sort of order of magnitude change. Again, boost clock frequency is only about 1.4 gigahertz. So again, about half of what you expect from a CPU. So for a MI200 AMD chip, this is kind of the equivalent diagram. There's a bit more detail here. The important thing to notice again here is you've only got sort of 2 levels of cache in the sort of center vertical lines in the middle. Do I have the ability to paint on? I do. Okay, so I have a cache here, and I have a cache here, and then I have some command process which is going to control everything above, and my memory controller is going to access my DRAM here, and then each of my compute units are these gray blocks. Okay, and they contain different arithmetic units. I have some set of program counters, and I have some local shared data. So this is local shared data which all the cores, all the stream processors can access. And I have an instruction cache every single on the right hand side, which is all of the compute units access the instruction cache and can share instructions across their threads, across their streaming processes. So this is shared set of instruction. Each stream processor is going to do the same instruction within a particular warp. It's going to get different data, and that's different to how we would operate a CPU. We also have constant cache, a small piece of memory which is shared more globally that everyone can access at this level. So you have shared data per compute unit, you have constant cache which you have shared over GPU, and you have instruction cache which is shared. Okay. So that's the GPU. What does the hosted device picture look like? So now we're starting to build up a node, a GPU node. This is the sort of setup you might sort of expect if you had a gaming PC, for example. The speeds and feeds are probably more related to high performance compute hardware, but the setup is you might have a single CPU on the host side with some amount of RAM on the host. So that's order of 10 CPU cores on one CPU. Actually, that's 64 on a CPU. You might have order of 100 gigabytes of memory bandwidth between that CPU and its RAM. You might have order of 100 gigabytes of RAM. Okay, on a high performance computer, you might do. On the GPU side, you have thousands of cores, and you have memory bandwidth, which is thousands of gigabytes, but maybe you only have tens or just about reaching 100 gigabytes of memory in the RAM on the GPU side. And then you have some connection, which is this host device transfer speed, which is order of sort of 10 gigabytes. That's getting faster over time, but it's still relatively the bottleneck. So the GPUs are hosted by a standard CPU. The CPU is responsible for the orchestration of the GPU's activities. In this context, the CPU and the GPU are referred to as host, the CPU, and device, the GPU. Okay, you'll hear this quite a lot. We'll use it. It will be important when you're writing transfer codes to transfer data between these two units, and it will be used quite frequently to refer to the GPU as the device. So you'll just kind of get used to that, to be honest. Modern configurations in high-performance computers are a bit more complicated than this. You tend to have a host, a single CPU, or maybe a pair of CPUs, and then 4 to 8 GPU devices in a node setup. I think I have a diagram next. Yeah. So this is the example. This is the sketch for the GPU nodes we'll be accessing on ARCHER2. There's this distinction between the 4 and 8 GPUs. There's a bit of history in there. Maybe I should add some additional slides into this, but this is a little bit long. Originally, one of the first high-performance computers to really go at scale in an integrated way for GPU acceleration was called Summit. It had 6 GPUs per node, and it produced. It's actually, I would argue, it was the earliest sort of exascale class computer. It's not really classified there. It didn't get close to an exascale of 64-bit precision execution, but it did get an exaflop of AI precision. Now, I'm not a massive fan of fractional precision flops because they don't have much use in the scientific domains I'm interested in. However, what it had was 6 GPUs per node, which is a bit of an odd intermediate state. And what this led to is this sort of 2-hemisphere. You had 3 GPUs that could talk fast to each other, you had 3 other GPUs that could talk fast to each other, and they couldn't talk across. However, the AI community really liked having lots of GPUs because at the time they weren't too worried about the communication power between them, and the scientific community was really annoyed because they wanted to scale out to many, many nodes working coherently, and if there was a communication bottleneck between GPUs, that damaged the performance of their whole application. So you end up with 2 communities wanting 2 different things, and therefore there's 2 major products on the market around GPU hardware. DGX, 8-way boxes, which we'll see quite common in AI data centers, and then this 4-way system that you tend to see in HPC systems. Mainly this is all around how you scale out, how you get N GPU nodes to work together to solve a problem collectively. The patterns in AI training are only just starting to get to the point where you want to have very large numbers of GPUs working on a single model together. Before you had data parallelism where GPUs could work separately and then communicate at the end of their particular training, their epoch or their training set. This has all changed with sort of these big NVIDIA Blackwell NV72 systems where they're trying to get 72 GPUs all linked very fast. Okay, this brings me on to this diagram. Okay, so there's 2 types of connections here between the GPUs. So at the top in green, we've got a little an AMD EPYC CPU. In our example, this is a Milan, slightly more modern than the Romes that are on the login nodes and the back end, the main CPU compute nodes of ARCHER2. And then we have 4 MI210 GPUs. They are connected together with a fast network called XGMI network, so they can communicate directly. They do not need to pass data back to the CPU and then back out to the GPU. This is a horrendous performance bottleneck, which early GPU hardware had. And luckily, we are no longer suffering from that. This communication isn't as fast as it could be. This is somewhere where NVIDIA is a bit better than AMD, is the speed between the GPU communication. But you can coordinate these GPUs to work together. Okay, so sorry, I will just look at the question. Yeah, XGMI is sort of the equivalent to NVIDIA's NVLink, in effect. I think they've changed the name slightly. It's now Infinity Fabric. They've gone through a couple of generations of this. The particular protocol here is XGMI in this generation. You'll hear AMD refer to Infinity Fabric far more often. I can't remember the name of the Intel equivalent, but it doesn't really matter because Intel are not really pursuing the GPU market at scale as they were maybe 10 years ago, 5 to 10 years ago. They very much suffered from the overheating and the power issues that we discussed earlier. That's why Intel are not really as competitive as they once were. Right, so the key thing here is there's different speeds of communication going on. the more you can avoid moving data back to the CPU to go back out to another GPU, the more performance you'll get. The system manager has 4 nodes, I think I mentioned that. We will have to submit jobs via Slurm to get access to the GPUs. There should be example scripts provided with the exercises. So, but there are no GPUs on the login nodes of ARCHER2. So you will have to go out and submit jobs to get stuff to run, and then inspect after they've worked. You can set up interactive jobs if you know what those are if you want to, but for these practicals, because of the number of people we have just enough GPUs for everyone, but we may see if other users are on, but they're not exclusive. We don't have a reservation for them. So try not to grab interactive sessions for sort of 3 hours. You will annoy your colleagues. Okay, so on ARCHER2, the scheduler, how the GPU is set up, we have 2 modes. We have a GPU shared and a GPU exclusive setup. You can submit jobs from the login node. You will need to do this from the work directory, so /work/TA217 that location. You'll have to move there once you've logged into ARCHER2 to actually get to the location. Basically, the home directory is invisible to the compute nodes on ARCHER2. If you submit jobs from the home directory, the scheduler will set things up, but then the compute node won't be able to see your executable. That's where it is. So yeah, we have these 2 different qualities of service. You can either have a shared where you can grab 1 node, and you can have I think it's a single or 2 GPUs. The idea here is so that more people can access, but you are on a shared node. So if you're looking at this later and you've got sensitive data, or you wouldn't want someone profiling and maybe getting access to information you had in your code, then run an exclusive node instead. There you can get access up to 2 nodes, and you can use up to 8 GPUs to work together closely on a particular problem. Again, this is just a test and development system, really. It's relatively small. It's to make sure that we have access and people can do some work, and we can provide training like this on ARCHER2. The CPU has 8 CPUs and 128 gigabytes of host-side memory allocated per GPU. So depending on the request of the number of GPUs you ask for, you'll get an even split of the host-side resources. Once you've allocated and requested your resources in the SREX script, you can use srun and assign how many MPI processors you want to run and in what configuration as you would normally to run on these GPUs. The usual example is you have 1 MPI process per GPU. It's pretty common. Okay, I've tried to provide a bit of some links here in these slides. I think these have been taken over. I can post these later around different hardware and details on the different generations of hardware. This is slightly, no, I think this is still just about up to date. I don't have Blackwell on here, for example. But this takes you all the way up to Grace Hopper in NVIDIA, and this takes you all the way up to the MI300X. So the world's largest and most powerful supercomputer, El Capitan, has MI300A and AMD GPUs as its main performance product. Okay, this is the second fastest is Frontier, which is an MI250X. So while NVIDIA may be the sort of brand that people are most associated with GPUs, actually it's AMD who are winning all the major high-performance computing deployments globally. NVIDIA do not yet, I believe, have a exascale supercomputer in the top 500, the world sort of ranking of high-performance computing resources. I believe that will change in a few weeks' time at Supercomputing Conference in St. Louis, because Jupiter in Germany will, I think, likely reach that mark by that point. Intel have, while they're no longer developing a future line of products at this stage, as far as I'm aware, the Max series GPU did go into systems like Dawn down in Cambridge, and Aurora was an exascale computer that's based out at Argonne National Lab in the US. Okay, so a very large deployment of Intel GPUs. We're going to talk about kernel approaches to GPU programming during this course. But there is a wider GPU programming landscape out there that I'm just going to make you aware of, where there are directive approaches, so OpenMP and OpenACC approaches, where you can take apply parameters to your for loops and have the compiler do the offloading for you. And really, this is a balance between the level of portability and the level of control. There's standard C++ now has some initial support in a branch for C++26, which extends some of its standard parallelism algorithms to offload GPUs. Raja and Cocos are portability frameworks which were developed as part of the Exascale computing project in the US to allow some portable libraries to target different GPU architectures in the back end with a single interface. The US spent a lot of money on developing a whole program of porting codes to GPU architectures when they bought their large systems in the last round. There was a decade-long program to develop these architectures. SYCL has also been started and supported by Intel. It also can target different GPUs as well and provides portability. And then finally, we end up in the sort of HIP, ROCm, CUDA environment. So we have far more control, but maybe we don't have as much portability in what we are accessing. Where does OpenCL sit in this landscape? That is a good question. I would probably put it around the SYCL area. I didn't think to include that. I do not have that much experience with OpenCL personally. I would kind of put it in that sort of SYCL zone in the middle. I have not had enough experience and exposure to the interface to give make a sort of case for that being. It's probably more portable, but it probably provides you low level of control of what you're actually launching it, where the data's moving, and things like that really impact performance. Okay, you can then start to talk about sort of portability, what the level of support is for all these different standards on the different hardware, and it's a mixed picture. It is at no point have we got sort of universal support. Okay, there are caveats across the space. Even if you end up in Python land, you're not guaranteed to get support completely across the board. Obviously, NVIDIA is a bit ahead of this because they started early, but just be aware, no matter how you go about programming a GPU, you will potentially have limitations on portability at this stage. Being able to program in this sort of level, this kernel level, will give you access to the most performance, but you may need to alter what you're doing in order to access different hardware targets. Okay, so that's still a mixed picture. It has taken 23 years to get here, though. So the first paper is dedicated to looking at sort of called shader metaprogramming, was sort of 2002. This is where you're using the shader libraries of a GPU in order to try and do some useful computation. So it does take a lot of time for this to develop and standardize. This is not really surprising. It took a long time for people to standardize with x86 and get MPI libraries to all be compatible. It's still not quite compatible with things like this. Understand what is actually required to do programming with new types of hardware. Okay, I've been talking for some time and we're going to have a break. I think I will keep going to the end of these slides and then we will take a 20-minute break or so. So we've talked about that's sort of been a general overview of hardware. What about sort of the programming model we're going to actually use in HIP and CUDA? So we don't really want to, as a programmer, worry about the exact composition of cores and compute units in the hardware. We want to use a nice abstraction so that we can tell the GPU, here's the data to operate and this is the operation to do. You distribute it. You decide how to do the latency hiding, how to get the performance out of the hardware, and how to utilize it effectively. We're going to have a description of that. We need a way of describing this in terms of a hierarchy of different threads and how to control these different threads. So we can dictate what can be done simultaneously and what has dependencies. And that's what this program model allows us to do. So if we have a one-dimensional problem, an array, for example, with individual elements, we can assign these elements to different threads or different streaming processes or CUDA cores, same thing, just different language, and they can be run and operate simultaneously. If I now wanted to have more than one group, I might collect these items of these threads into work groups. I can then schedule these different work groups to operate on a compute unit and do work simultaneously and be operated on by the GPU. So a one-dimensional picture of a work group, or in NVIDIA terms, this would be a block, might look something simple, something like this. I might have thread 0 to n executing on block 0, and then a different compute unit or a different one might operate on block 1 from 0 to n, and then another block. And this can scale up to the number of blocks I have. And some blocks can wait until there's hardware available to process it, and then it will operate. But I can describe how I'm going to organize my work to be done and split up over the available resources. So a wavefront is a subset of a work group. It is designed to execute a single SIMD, so single instruction multiple data unit. But in AMD, this might be 64 threads, all operating the same instruction, but we allocate the different data to each stream processor or thread in order to do work, useful work. So wavefronts, these subsets are mapped to compute units for execution by the hardware scheduler. So we typically, as the developer, decide the number of wavefronts work groups based on the problem size to be distributed. Okay, and that's going to enable us to get good performance out of the hardware. So we have to make a decision for our particular problem or our particular piece of code or algorithm, how we're going to decompose in order to get use of the hardware. So this naturally extends to 2 dimensions. So now we can look at blocks which are 2-dimensional. Again, this is very obviously related to this sort of rendering problem in graphics. I've got to render a 2-dimensional screen, I've got a 2-dimensional plane of pixels, but there's also an extension to 3 dimensions as well. Okay, there's support for that as well. So we can start to deal with the whole, sorry, what was I going to say here? Yes, this is referred to as a grid. Okay, I have a grid of blocks. So I have this hierarchy of grids contain a number of blocks, and I've got a number of threads that can operate within a block. So HIP was developed by AMD. So this stands for Heterogeneous Compute Interface for Portability, which is a bit of a mouthful. It's a runtime API and kernel language implemented in C++. It enables developers to create applications that are portable across AMD accelerators and CUDA devices. So HIP does allow you to target NVIDIA GPUs as well. HIP has 2 distinct types of source code, and this is important: host code and device code. Host code is essentially the CPU, is code that the CPU executes on the host. Okay, a bit obvious, but this is C++ code that incorporates all the standard features. So it's entry points for execution of main functions. It's facilitating tasks like allocating, generating buffers, managing data transfer, executing kernels, and kicking off kernels to be executed onto the stream, moving data between host and device, things like this. Okay, it's about the control of the execution. The device, typically a GPU, executes device code. Okay, this has a C-like syntax, and we can write kernels, okay, that encode operations to be done on the device, and then we launch those kernels with the host call. Okay, so instructions from the host are queued into streams for execution on the device. This is asynchronous, which is really important. You're not logged into the GPU running execution. You're going to queue up work for the GPU to do. This can make it challenging. This is something that makes GPU programming challenging because debugging and order of execution and things like this can become more challenging because of this asynchronous nature of this programming model. This is also why we refer to the GPU as device often, because you could also use the same model without a GPU being involved. You could have another type of device. You don't see it very often, but that's really where this sort of language comes from. Okay, compilation is a little bit complicated. Effectively, you have to have two compilers that are going to operate together in order to compile your code. So HipCC is a compiler driver utility that calls AMD Clang or MVCC, NVIDIA's compiler for CUDA code, to compile HIP code. Okay, so depending on what you're targeting with the back end, HipCC will work out what you're targeting based on some information you provide. But for our course, we're just going to focus on AMD GPUs. So you can think of it as this HipCC is going to compile the HIP elements of the code. HipCC is included in the AMD ROCm stack, software stack, that you can access and download yourself. We've installed modules on ARCHER2, so you can load the modules. We'll show you which modules to load in a minute. Yeah, so the HipCC compiler compiles both HIP code for the GPU execution and the non-HIP code for CPU execution. What it's actually doing is underneath the hood, it's got a CPU compiler that it's pointing to. And in some cases, you might want to switch out which CPU compiler that is, and there's commands to help you do that. But for now, we're not going to touch any of that. Just think of it as a compiler to do the orb to everything. You can use HipCC -- help to list some options. And to compile code, we're going to run HipCC -x hip and code. So what you call this -x function is effectively to say, go into the files provided and compile everything. You'll find HIP code in here. Don't expect the HIP code to be in a special separate file. So you could organize your programs to separate out kernel code and the GPU code into separate files, which are got an end.hip or .cu or something else like that. And this -x flag saying it's all going to be in the same file. Just look in there and run both passes on the same file. So it's going to compile GPU code and it's going to compile CPU code in two passes. If you want to see exactly what it's doing, you put pass the -- reverse option in, and you'll get more information out. Okay. Is it common to see both codes separated out? It entirely depends on your decision. I've seen it be less common. In my experience, again, it is entirely how you decide to write your code base. Trying to think of an example where I have actually seen it done and I'm struggling to, which might be the answer to your question. Okay. The other important piece of compilation is that depending on the generation of GPU, the physical hardware, the compute unit, or the streaming multiprocessor will have different underlying architecture. So we need to provide details to the compiler about what this architecture is. If you don't provide this information, it will compile for all, usually, which means it'll probably still work. You just might end up with a very large executable. You can think of one of the motivations for this will be is the fact that you will often be compiling this code on nodes which don't have these GPUs attached. So the login nodes in ARCHER2 right don't have GPUs. So you need to tell it exactly what it should be compiling for. In HipCC, this is done through this offload-arch flag that you need to provide. So you can see kind of this line. Sorry, my little highlighting up again. This line here. And depending on the architecture, you're going to have a different Arch code. So you can see on this diagram on the right, if I had an MI50 GPU, it's quite old now, that would be GFX 906. If I had an MI100, it'd be GFX 908. And then for MI210, MI250, MI250X. MI250X is what's in Frontier, the world's first exascale computer. It's this code, it's GFX 90A, which tells you that the fundamental architecture within the GPUs in ARCHER2 is the same as the ones in Frontier. It's just, whereas in ARCHER2 we have a single sort of unit per GPU, and Frontier there's two. Okay. And there's some more documentation about different specs. So if you come and I haven't listed the MI300X and 300A equivalent codes for this, so you can look on the documentation at the bottom to find that if you want to. So we've talked a bit about portability around CUDA and HIP. They're very equivalent APIs. So they're not equivalent, they are very close APIs. CUDA was ahead in this development, and effectively, which is quite luckily for us, AMD didn't try and reinvent their own API. They quite smartly said we're going to they didn't say this, but what they did was they effectively copied the CUDA interface. So most of the function calls have the same signature, which means by doing and looking at this course, you should be able to program CUDA as well as HIP. Another useful tool if you want to convert between the two, what's called Hipify. This allows you, if you're interested in porting to a high-performance computing system which has AMD GPUs, but you have a CUDA code, you can run Hipify in order to try and do some code conversion across into HIP code. This can be quite beneficial because you can use HIP compilers to target CUDA. Again, these vendors are not working together, so the level of support there may not be perfect, but there is an option to always compile from HIP code to CUDA. There isn't the reverse, unfortunately. But you might be able to use Hipify to get you a version of the code which you can compile for a particular AMD system. So if you wanted to take a CUDA code and try out here, you could run Hipify and then compile it for these GPUs. Okay, so that was quite a long talk. We're going to take a break now for 20 minutes. The goal really of the program is to describe the problem in an abstraction, if grids, blocks, and threads, to be able to pass the particular problem into the GPU. The hardware is then free to schedule the work as it sees fit in order to minimize the high latency to get the best performance out of the system. That's operated by the runtime, GPU runtime. We've talked about the basics of scalable parallelism in architecture, and we've shown some examples of GPU architecture as well. Yeah, so as I said earlier, the very latest HIP programming guide is at this ROCm docs AMD.com projects HIP and its latest, or if you want the documentation that aligns with the particular version of ROCm we have at ARCHER2, this is a ROCm docs AMD and it's docs-523. That is all I had for this session. I will stop sharing so you don't have this horrible positive thing going on. Okay, question. Yeah, I can provide access to this presentation. I think the course material has a GitHub Actions set to generate a page. I think the material has been copied across into that recently. If not, I will provide it. So what we'll do is we will take 20-minute breaks and we'll start 20 past 10 again, because I've talked for quite a long time and you guys probably want a break, as do I. We will then start with an exercise looking at memory movement for the remainder of this morning. Okay, so thank you very much. We'll return at 20 past 10. Okay, if everyone's back, could you please just put a +1 in the chat to say you've returned? Great. Fantastic. Okay. I think that's most people. So we will get started again. What am I doing? I'm going to share this screen. Okay. That's what I should have said before we move on. So I've provided the link to the GitHub some time ago in the chat, but I'll provide the link to the lecture site. So this is the GitHub Pages page, which is generated by via that GitHub account, via the GitHub repository. So you can look through some of the slides there. They're not exactly the slides I had earlier, but for the rest of the material, we're using this. So I'll provide those slides separately. So what we're going to do to finish off today in the last 40 minutes is we're going to look at an initial example of doing some HIP programming. Yes, that's what we're going to show. Okay, Jeffrey, can you see that clearly?
Still loading. Yeah, I can see it now.
Great. Okay, fantastic. Okay, so we talked about our host and device model. Now, how do we program in this host and device model? So, main thing here is we have to assume that there are separate address spaces, memory address spaces on the CPU and in the GPU memory. Okay. This means we really need to consider carefully about how we allocate memory in those two spaces and how we move memory between those two spaces. And this is a really key consideration for both correctness of programs and performance, about how we do this and when we choose to do this. In some more modern hardware, and this is a particularly confusing point in the history of GPUs, is many times the word unified is bandied around unnecessarily. Okay. In the AMD MI300A and the Grace Hopper and the Blackwell GPUs, there is now unified memory, as in there is a single address space for all the memory on the GPU. Okay. So you will hear unified maybe mentioned before in other literature. That is the hardware implementation of unified memory. There is a single address space you can access. We're not going to make that assumption at the moment, okay, because we're going to need to deal with GPUs which don't have this capability. So we're going to treat them as separate address spaces, but be aware people are starting to implement them as unified places. This does not mean that they have uniform access speeds, okay, and this is very important for performance. They may well provide a single address space, but depending on where in that address space the memory sits, the speed at which you can access it will be different. Okay. So we want to start programming and moving some data from our host to our device to be able to use our GPU. What do we need to start including in our file to start writing a piece of code? So you will need to include in a C++ source, might start with hash include hip/hip runtime.h. This is usually relevant for programs compiled by hipcc. There's also a subset, which is hip runtime API, which is just the C++ interface, so you don't need to compile it with hip because it's not going to compile the library functions that are going to call. It's just going to give you the function definitions, which can be linked in later. So memory management, data access by kernels, the unit of execution on the GPU, the thing that controls the instructions about what we want to do, the operations we want to do with different threads. The data accessed by these kernels must reside in the device memory. Sometimes also referred to as device global memory or just global memory. Okay, I would really try and avoid using the phrase global memory. I think it's just confusing. So device global memory to refer to as sort of like the GPU RAM. Okay. There's different ways of allocating and moving data between host and device. There's two main methods we're going to discuss. It's explicit allocation and explicit copies, which we're going to focus on first. And then in a later exercise, we're going to look at managed memory. We're going to manage memory, makes your life easier for the programmer, but it potentially has impact on performance. Explicit allocations and explicit copies are better for our understanding of the hardware and getting performance. So we're going to focus on that to begin with. Okay, so let's start with allocation. So a variable that references device memory is declared using a C++ data type and as a pointer. Okay, so this double star data is a subpointer we set to null initially, but it's going to tell us about where we're going to use this to refer to data on the device. Okay, so this is a pointer, an address in memory that is going to an object that holds an address in memory, which is going to refer to which is going to live on the host, and it's going to refer to memory on the device. Okay, so I can have host side pointers, which normal pointers on the host would be I am a pointer that lives on the host and I hold an address which lives on the host itself. If I dereference that host side pointer, okay, that holds an address to the host, I will get a memory location I can access here on the host side. This is a slightly different version of that, where what I'm going to do is I'm going to hold an address to memory on another device, which means if I dereference this on the host, it's in a location which makes no sense to me. It's not a location I know about. It's in an entirely different piece of hardware. So in order to get this address and hold it within this host side pointer, I must use hip malloc in order to allocate this location in memory on the device. I can't just call malloc. Malloc is going to be a location on the host. I have hip malloc to allocate me some memory on the device. It has the same signature you kind of expect. I provide a pointer and I provide some some size of data I want to allocate. So an array and the size of a double. So I'm going to have n array number of doubles allocated on the GPU on the device. This hip malloc, when it runs, provides an error code. So I can see whether that operation completed successfully on the device. If there wasn't an error, there wasn't an issue trying to do an allocation, I had space available to me to do that allocation and it was all fine. So I have that error code being returned. And there's some issues with what's exactly written there. We'll come to that in a second in terms of what we're doing with that error code that's returned. So in my application, I then might perform a load of work based on that memory location on the device. And then later I need to free that memory location on the device. So I have to call hip free on data. So provide the location that I wish to free. Again, it's a hip call to free because it is going to happen on the device and free that device memory, not my host side memory. Okay, I've labeled that point a little bit, but it's an important distinction. So now we've got a location on the device in which we can access, we've allocated some memory. We now want to move some data to fill it up. Okay, we're going to copy data from our host to our device. And we can do that with the function called hip_mem_copy. So this is the signature of this can be read as in destination, home source, the size of the data to be transferred, and the type of transfer we're doing. So the direction. So this is hip_mem_copy host to device. I'm moving data from my host side, my CPU memory side, over to my GPU, my device memory side. I might do some useful operations on the data I've copied, and I might want my result back. It's pretty useless for my result to sit remaining on the GPU where I can't see it, I can't save it, or if I can't get it back from there, then it's not very useful to me. So then I also have the reverse setup. Now notice that two things change here. I'm calling the same function, but because I'm now wanting the data to come back to the host side, I'm calling, this is going to be the destination is host data. Now in this case, I'm overwriting whatever might have changed on the device. This means that I'm going to write back to the same location I copied from, so I will overwrite. I'm going to the source of the data is on the device. That's still the data location if I've updated that in place on the device. The size is the same. I want to copy it all back. Don't have to copy less than all of it. And then I've changed the kind of copy I'm doing. Here I'm saying I'm doing device to host. Okay. These are all blocking calls. They will not return until after the transfer of data has been completed. So this is referring to the asynchronous nature of, or this is synchronous. Sorry, the nature of how this flow execution will work. So it will block further execution or operation until these operations have completed. So you've got an ordering occurring. The signature is below. Like I said, this also returns an error message. And as you can see, I've got some destination, source, size, kind of copy. So I said I'd come back to error handling. So most HIP API routines return an error code of a type HIP error_t. So this is an error type. It is important to check this code versus HIP success. And what you want to do is make sure that if it's HIP success, it's fine, continue the program. If it's something else, then report it and give us some information. Because if you're going to get an error, you're not failing on the host side, so your ability to inspect errors and things like this is all happening on the device. So are you going to get this information reported back? If you have some crash or issue with the function, it might just fail on the device, and you may get very limited information back to the host about that failure. So in checking errors is incredibly important if you want to remain sane, frankly. If you want to make your life debugging your codes easier. So when you return this error code, you can inspect it. So you can get the name of the error and you can get the error string by calling these two functions. So hip get error name and hip get error string from the error return code that's been returned from each of these functions. In practice, we've tried to make life a little bit easier. So in the examples we give, we've provided this macro called hip assert. But we wrap these functions in. And what this is going to do is it's going to call a function that checks that error string and provides a print statement of the error name and the error description if the error is not just hip success. If it's hip success, nothing gets printed, the program continues. If there's a problem or something different, it's then going to print a little information and stop the program there. This just helps to avoid clutter. But as you go through and you're implementing your own calls, I would remember to add hip assert because it will help you debug issues throughout the examples we give. And the code for hip assert is provided in the example box of code. Okay, I've talked a lot already this morning, so it's time to get you guys to do some examples. What we'll do for the remaining sort of 30-35 minutes of this session is get you guys to work through this data transfer example. And then at the beginning of tomorrow, I will work through it myself and show the answers. So if people get there really quick, great. By all means, feel free to finish up and if you've got other things to do. If you're finding it takes a little bit longer to get the handle of it, you've got some time this afternoon or later on to have a go and try a little bit more, and then I'll talk about the results and how to approach this tomorrow morning. So important things to comment on really with this is when you are compiling on ARCHER2, you want to load this set of modules. So programming with AMD sets the right program environment, sets the right default compilers for to be able to compile the HIP view. We're going to load ROCm, which is going to give us access to HIP C. We are then going to want to set this Crepey Accelerator AMD GFX90A. This is talking about the particular architecture in the background. So it sets some environment variables to make sure this is getting assumed in the background. And we have an equivalent one for the CPU side. Now this doesn't normally matter, but just so we're complete here, the default is set for the ROM chips on the login nodes and in the main CPU compute part of ARCHER2. The GPU nodes in ARCHER2 are slightly different, they're slightly more modern. They have Milan CPU part, so you can also set this particular variable as well, which I would just to complete this. So you're going to need to load these 4 modules, and then here is the example compile line you'll need to run to compile this particular example. So there's a number of things happening here. So you've got HipCC, you're using -xhip, which means that the CUDA code can sit within the same file as the C++ code you'll be writing, so we don't end up with multiple files. To be honest, this is really done to simplify the organization of these examples. You're going to have a ROCm path, which is going to be set in the background by these modules for you, so it knows where to find ROCm. You've got some environment parameters to set around the ROCm type of the platform. We need to provide our architecture. So this, again, we're by hand setting GFX90A, which tells HIP to compile for the GPUs we've got on ARCHER2. And then this is the executable. Okay, this will produce an A.out file for you that will run. The Slurm script is set up to run an A.out file to the directory. You set this up and we'll get it running. You can make it nicer by providing an output file name and changing the submission script to run the code. Okay, that's the compilation step. I've provided the link to the slides here. What we're actually going to be doing then is looking at the example. So let's answer this question. Is it? That's annoying. Why is that broken? Page not found. GitHub ARCHER2 Git Pro 1 data transfer. I think it. I'm just trying to find the link that you clicked there in order to get to the right location. Oh, it's this link here. Yeah. Okay. Right. That sounds okay. Okay. I will post the correct file there. Yes, that needs updating. Apologies for that. I was just going to go over to the GitHub in a moment and show you the exact files to look at. But yeah, it should be linkable. Okay. So initially, so all this is doing is nothing clever. first, get on and compile this example. It won't, and get it just to run. It won't do anything fancy. And the main thing you're looking at here is you're going to have some device. The maximum number of threads per block is going to be set, and you're going to get a result, which is number of elements 256, and the number that are correct is going to be 1. Okay, because the first element is going to be right regardless, because it's expecting 0. I think it's by default 0 or something like that. You're then going to need to update the code in order to transfer the data effectively, and there's comments in the example code in order to do this. So if I go to, that's not what I'm showing. This is the tab I'm showing it in. Okay, I'm just going to go to the example page. Okay. Okay. So size is. Okay, yes. So this. This is the correct location. Yeah, as you said, that's the right place on the source tree. So clone the files over to the work directory in ARCHER2. So you'll need to be somewhere within /work /ta217 /ta217 /username, that location. Users, I'll leave that slide with the compile instructions up for now. Try compiling that example and get it to run, and then try to follow the instructions in the file to update that in order to do data transfer and get the elements to basically of the initial vector to be moved across to the device and then moved back to the device. Make sure that you check errors, make sure that you are creating the right type of pointers, and make sure you're freeing any allocations you do on the device. Okay. I've linked again the slides from this session, which should have all the example bits of code you might need to pull in. Me and Jeffrey are here for the next 20 minutes. We can be here a little bit longer to answer any questions you might have as you try this out. Don't worry if you don't manage to complete it in this time period. We will come back tomorrow morning and look at the answer before we start the next section. Okay. That location should exist. So if you have a user set up in this project, which is how you should have come in, I'm just double check I've actually given the right location now. Yeah, so for example, this is mine, for example. It's not a problem if you're coming in from a different project and you haven't set up this particular account for this particular project. It's not an issue. You might need to. You just need to be in the work space. You will also need to pick a budget code, which is. Have I come in the wrong project? Have I been particularly smart? Yeah. Okay. It doesn't matter if you're on a slightly different one and this is a previous example. That's fine. We try to keep you in the same training account, ideally. But if you're coming on an old one, then that's not a major issue because we don't have a reservation assigned for this particular training course. Yeah, the username just needs replacing with whatever your username is, obviously. The only way it would affect is in the Slurm script to submit it to run on the GPU nodes, you might have a you'll have a budget code. I'll actually just share that really quickly to show you, because there's something else I can show you at the same time. That's what I was going to do. I was going to close the repository in front of you so you could all see that. Make sure everyone's happy, but that's fine. We will survive without that. The assert is just checking that pointer, I think it's just checking that's a non-zero value, so you actually get some host memory allocated. Pretty sure. Okay, I will share this briefly just to make sure everyone's seen this. Okay, this is the location of ARCHER2. Okay, I've logged in. I'm going to git clone the repository. I'm going to go into this directory, and I'm going to go into section 2.0.1. Okay. In here's the file that you want to look at, and you've got to make fun of things like this. But you also have a submit. Okay. We don't actually need a assignment. That's fine, because we don't actually need an account because the GPUs are free to access on ARCHER2, so don't worry about account updating. But you can see here where we're using the quality of service shared. I talked about this earlier. We're using GPU partition. We're asking for one GPU. We're asking it for a minute because this is very, very small. And then when we're running it on one GPU, one task, and we're asking for one CPU. We're not asking for very much results. The other key thing to mention here is ROCm SMI. This is a nice tool that can give you statistics about your GPU. I don't want to distract you too much now in case you have questions on the example, but that can be quite useful, and I will show the results of that tomorrow morning, just to inspect whether your GPU is actually doing anything. It's quite good for just checking it's actually done the thing you expect it to do. Sorry, you think it's not what you expect it to do, but it's done some activity. That's what you're really asking there. Okay. You can look at the make file. I would advise you ignoring it for now. You can just run make, that should build it, but I would get used to writing out the painful command line bit yourself. Make documentation. Yeah, the module loads the command line directly. Yeah. You need to run those. No, you don't need to add a budget code to the submit script. My apologies. I forgot that we do not charge for the GPU access. It should run without. You can put this set of 4 modules into a little script because you're going to need to rerun it every time you get onto the system in the next 3 sessions. And remembering the correct incantation can be useful. They're also on the ARCHER2 documentation if you forget it as well. My reason for being persistent about you guys doing this by hand, the HIP compile line setup, is because especially for GPUs, depending on different hardware, different versions of software and things like this, or there may be magic incantations for variables you need to set, they often get hidden away in make files, and you don't get an understanding of what the type of parameters you might need to activate. And depending on different GPU systems, the specific set or combination you need is a bit like the magic formula, which someone knows down the back of the sofa. But knowing the type of things to try out means you can work them out yourself relatively quickly. But if you're used to just hitting make and getting to build, then you don't get a sense of what the type of things are. So just setting the architecture correctly can be very important. In NVIDIA speak, there's a thing called a gen code and a compute capability. And you can start to, and if you don't set them, it may well compile, but if you require certain library combinations, there may be dependencies you don't know about, things like this, which cause breakage. We had an example of that very recently on Service Desk. Yeah, are you actually submitting to the queue when you see that error, or are you running the script? If you just run the submission script, like / submission script or source, it'll say, you won't actually submit. Yeah, good. Okay, good. That's fine. Don't worry. Okay, great. Yeah, and but this demonstrates a really key point. In a lot of these systems, the login nodes don't have GPUs, so it just goes, I have no idea what you're talking about. I don't have the drivers available to run this code, and you get very cryptic looking errors that are like something's gone weird. Yeah, great. See you tomorrow. We'll pick up from this and start looking at kernels. So, sorry, there's a few questions there. I'm just starting from the top. So, Huang Dai, you had an SBatch error. Could you let me know which project you're a part of here? Are you running as part of the TA217 or a different project? Because if the project doesn't have the only reason you should get that error is if the project you're in doesn't have any allocation, right? You have to have some non-zero balance to run, and that might be why that's occurring. So if you let me know which project number you're running under, then that will help determine that. Right, why is error not declared here, and what type should it be? So error is not declared here because it is just a code snippet. Yes, it's bad form, it's just not declared. It is on the next slide. So I'll just go back to the slide. It is of type HIP error T. That's the type it is. Okay. So we will end there for today. Okay, if anyone has any questions in the intervening this afternoon, by all means send me an email or send a message, and I will try to get back to you. If not, have a good afternoon, and we'll start again tomorrow at 9:30. I will go through this example, and then we will move on to another exercise looking at writing our own kernels. Hopefully it was useful, and I hope you found that valuable. See you soon.